This presentation concerns the use of LLMs in reverse engineering, and we reverse engineer programs in Java and Python to the object constraint language specification notation. And the aim is to use the wide knowledge of an LLM together with precise rules to produce accurate reverse engineering of a wide range of programs. So reverse engineering in general tries to analyze legacy systems, to produce documentation, also to support re-engineering. And a common specification notation for representing programs is OCL and UML. And why should we use LLM? Well, an LLM is a large language model. It's a specific kind of deep learning that embodies a wide range of knowledge, and particularly programming knowledge. Our contribution is to produce a data set of pairs of Java and Python programs and their corresponding OCL specifications, and we use those to fine-tune the pre-trained LLM, Mistral LLM, to produce a particular kind of OCL that's useful in re-engineering. The precise rules that we use are those encoded in the Agile UML toolset. They go from Python code elements to UML OCL elements, and also Java to UML OCL. And then that precise rule set, rule-based approach is used to produce OCL from the selected Java and Python. That produces a training data set for the LLM, and then a standard inference process is used to apply that to new programs. So far we have 1,000 pairs for Java and 1,000 pairs for Python. That's being enhanced. And we took the sample programs from a widely used dataset, Avatar TC. We used the Mistral LLM for reasons of efficiency and cost, and we used the quantized LoRa approach. Then there is pre-processing and post-processing, for example, to remove clearly invalid output, to improve the quality of the output. For the LLM, we used a fairly standard set of prompts to ask it to produce OCL from source code. And to evaluate, we used measures of accuracy and consistency, otherwise expressed as recall and precision. Accuracy reflects how much of the source is accurately represented in the target, and consistency concerns how much of the target is originating from the source. In other words, we want to minimize spurious elements. And combining those two gives us an F score. And the baseline is the untrained LLM without fine-tuning, and the LLM for models is after fine-tuning, and we can see a generally improved accuracy. The aim is to produce specifications that are quite explicit. They can be used to produce a new version of a system in a different programming language, and they explicitly represent the semantics of the source. So here's a little bit of Python, and the desired specification is an explicit specification in terms of library code that's defined in Agile UML. If we didn't use fine-tuning, then the LLM produces quite general specifications which express generally the idea of the program, of the source program, but they're not useful for forward engineering, and they're quite implicit often. So the fine-tuning improves the utility of the reverse engineering process. So our contributions is to produce an LLM-based approach for reverse engineering, and it produces specifications from code, and we've shown that this can produce benefits, in particular over an untrained LLM that has big programming knowledge, but it doesn't have the precise rules to produce a useful specification.